Good morning, everybody. We are going to continue our lecture on the differences of bond types and how to predict them. Now, this is a little bit of a scale in terms of we are talking about nonpolar, polar ionic. If you can remember, nonpolar, we're talking about that tug of war where they're sharing their electrons exactly the same, no one's winning the tug of war. Polar, they're also sharing their electrons, but one side is a little more electronegative than the other, and that's why you can see this little bit of a change here. The difference in electronegativity, you should have a gold sheet for that. And then as it gets larger, we have an ionic where you have a transfer of electrons. I wouldn't really advise you that you need to memorize these at all. I would just need to remember that if you have a zero charge, that is going to be nonpolar. And then as the electronegativity gets larger and larger and larger, then you're going to have an ionic structure. Now, for the most part, this is a guideline anyway. There's going to be tons of overlapping, and most of it's going to be determined by their shape, which is what we're going to talk about later in this chapter. So for the most part, just take a look at, yes, I can subtract their electronegativity values. If it's really, really low, I have a nonpolar substance. If it's very high, I have ionic. So this leads us to bond polarity, and we're talking about a dipole moment. So a molecule with a center of positive charge and a center of negative charge is called a dipole, or said to have a dipole moment. We will talk about dipole moments a lot in here. So you can see that I have hydrofluoric acid here. Fluorine we know is highly electronegative. So they show this electronegativity by a charge distribution that the electrons are moving slightly closer to the fluorine. And so you can see that this would be written as a positive charge. This would be the negative side. And so they just connect this with an arrow, and that's how you often see electronegativity. So this is said to have a dipole moment because there is an uneven pole. So this would be a polar molecule. Can you have a dipole moment with something that's nonpolar? No, you cannot, because remember that tug of war, no one is winning. So if we take a look at the electrostatic potential, all that does is show you the electron density. You can see by the color here that this orange-red is going to be the rich area of electrons. Now, you have to keep in mind that these electrons are constantly moving, but the probability states at any point in time, we have a higher probability of finding an electron on this side of the fluorine because it's highly electronegative. So this is the blue region. This is very poor. Again, they're just using the Roy G. Biv, the visible colors of the spectrum, to display this. So as we take a look at distribution in water, you guys should recognize, if you take a look, that oxygen is much more electronegative than hydrogen. We put in this electric field here. It should make sense to you that the hydrogen is going to attract to this side, the oxygen is going to attract to this side. So we're kind of combining all these concepts that we just talked about. And so my electronegativity is going towards the oxygen, which again is shown by my electron density being more on orange over here. And so this is just the way that this is orientated. So asymmetrical molecules, polar bonds, will have a dipole moment. Again, we're starting to bring in asymmetrical, meaning their shape. You can see that if I look at this in half, that I do not have the same orientation on both sides. And so this is asymmetrical, polar. Someone's winning that tug of war. There's going to be a dipole moment. Now this has to do with how easy or difficult it is to break some of these bonds. Again, this is ammonia. We've talked about ammonia. Ammonia is NH3. And if you recognize NH3 and how we would draw it, is that it has a lone pair of, these are a lone pair of electrons up here. And I have hydrogen that's distributed evenly around this. This is going to be an sp3 hybridization, which we're going to talk about in a little bit. So you can see that I have my hydrogens are slightly positive, my nitrogen is slightly negative. Again, they've induced this battery to show you that the molecules are going to rotate themselves, and here is its electron density diagram. So does this have a dipole moment? Yes, it would have a dipole moment because there is a differences in their charges and how they are aligning. How about carbon dioxide? It doesn't look like it. If I look at my electron density, you can see that it's the same on both sides. I have the same thing pulling from this side as this side. No one's winning the tug of war. The flag is staying right here. If this was my mud pile, no one is going to be going into the mud. So this does not have a dipole moment. It is symmetrical, with polar bonds will not have a dipole moment. So they are still sharing their electrons like we've been showing all along. This is symmetrical about the central atom, around the central atom, and so it does not have a dipole moment. All right, so now our ions and ionic substances usually refer to the solid state. The ions are packed very, very close together. We've talked about how they've just been vibrating. We talked about it the day that I brought the dry ice in, how they just are very close to each other. And again, you can see that they have a negative and then a positive and then a negative because of how these are going to interact with each other. And as you draw that out, can you see that I have a shape of a crystal? So something like NaCl is something that will fall apart on its geometric lines. And so if you were to tap a crystal, if any of you have ever grown crystals before, that's why they grow in certain geometric shapes, is because they're very tight around each other, attracted to the different charges in an orderly fashion. All right, isoelectric is ions containing the same number of electrons. Well, if I take a look at this, I have oxygen that has the atomic number 8. Well, if I lose those or gain those 2 electrons, it would have 10 electrons. Fluorine has the atomic number 9. That means it has 9 electrons. Gaining 1 more is going to be 10. Sodium has the atomic number 11. It's losing 1 electron. Magic number 10 again. Magnesium, atomic number of 12. Loss of 2 electrons. Has 10 electrons. I think you get the picture. Aluminum has 13, it's only losing 3 electrons, and it's going to have 10 electrons. So all of these have 10 electrons. So how do the size of these ions vary? If you take a look on the periodic chart, all of these now have 10 electrons, which is going to have noble gas configuration. The noble gas configuration of neon. Well, can they all have the same chemical stability? The answer would be no. So we have to take a look at how these vary. So if I have anions right here and I have cations here. This is a really, really good section for review. By the way, this is on page 341. I would make sure that I go back and read this. But you need to remember that cations are going to be smaller and the anions are going to be larger than its neutral atom. So if I take a look at a cation of sodium, sodium has lost this 1 electron, so if it's a +1 charge, it's going to be a smaller in terms of its size versus its neutral atom. And the reverse is going to be true for anions. So if I'm going to bond this with an anion of fluorine, so fluorine in its neutral state is going to have a certain size, but then I gain that 1 electron and it's going to be a larger ion. Is that going to affect its bond charges, and it's called lattice energy? Absolutely, and how these come together. And that's what we're going to go through in the next section. So again, this has to do with the size of the radii, and I would make sure you go ahead and check that out. Okay, I think that's all that I wanted to talk about. Remember, these have general trends, and these are called isoelectric ions because they all have the same number of electrons, but they still vary in size, which is the point that you want to see here. All right, I'm done with this section. Have an awesome night.